Better show up. Something else. I mean,
Richard, sir.
Wow, what is it? Coke?
Vote.
Vote. Oh, I've already voted. Right. So I do want to do an exercise today on the computer. So if you have your laptops, want to boot them up and start up the Composer Studio. I'll lecture for a few minutes to allow your laptops to start up. Bring up Code Composer Studio. I do want to, before we do the exercise, I want to show you an easy way to write assembly language functions. So, but two other topics I want to talk about from the textbook before we do that. And again, at this point, I'm not actually requiring you to do any work in assembly. He's got, in the textbook, most of his examples are in C and assembly. You know, we'll work entirely in C, but yeah, you can learn a lot about C by digging into assembly. So in C, you can, and certainly in assembly, you can pass parameters in two different ways. You can pass by value, and this is up to you as the programmer. So what this looks like, for example, would be, say, 0. And then here we're going to call a function where we pass this value by value. And the function would look like this. So it doesn't do anything more than increment its input arguments. So in this case, so it reads this value of v and increments it and returns via the return parameter the incremented value. So in this case, if we printed out val after the return, it print 1. Okay. But the v in the program here is a copy of the argument. Okay. So if we change v in the function, has no effect on the value in the original program. So to change the value, we actually have to, in this case, return the value, and then we make the equate it to val in the original program. So the other way that you can pass arguments to in C or in assembly is, they call it pass by reference. It's really passing by address. So simple example to do the same thing. Equals 0. Increment v2. And then here I'm actually going to pass. So the ampersand would say take the address of. That's the address of. So take the address of, and val would be on the stack here, because it's a local variable. So it would say take the address of the item that's on the stack and pass the address now to this function, v2. And we have to indicate that actually now what we're receiving is an address or a pointer. And we don't actually return anything. This is a void function, actually. But because we have the address, we can dereference the address. And actually we can dereference the address and increment that. And that will directly affect the value in the calling routine. So, we've got these two different ways. Passing by value is safe. In most cases, especially in a library, someone who uses your library routines, when they pass a value, the library should be documented, but they pass a value, they don't expect it to be changed by the calling routine. If it does, it should indicate that in the documentation. But passing by value is fast for small data sets. We've seen how on an ARM processor, the standard calling convention is to put the input parameters into registers. So there's no faster way of passing arguments. We can pass arguments by actually pushing them on the stack too, but that's slower. And certainly if you have large structs, passing them by value where copies are made, that can be slow. Now, passing by reference allows you to use parameters as both input and output parameters. Your C restricts you to actually one return parameter. Now, it could be a struct that contain pointers to other parameters, but you're restricted to one return parameter. But if you use reference, and pass by reference, you can use all of those arguments to make changes back into the calling program. And then passing by reference is fast for large data. Again, if you pass an array, it's automatically by reference. And in C++, objects are passed automatically by reference as well. You can use global variables to pass data to functions. That's not considered to be good practice for a long list of reasons. Just Google "don't use global variables" and you'll see a long list of reasons why, in general, you should avoid using global variables. Because once you use it as a global variable, it makes it difficult to use the name. You lose the concept of locality, of making changes to a variable only in a function. They could be made by any function that has access to the global variable. So generally, we try to avoid the use of global variables. Sometimes you have to. Okay? Sometimes we'll see that a standard technique for passing data between an interrupt routine and a main routine is actually use a global variable to do that. We've also talked about parameter passing in C. There's a different standard for every different microprocessor. For the ARM processors, we've seen that the first 4 parameters are actually passed in registers. The return parameter is in R0, whether it's a value or a pointer. Additional input parameters have to be passed on the stack. And you're free to use R0 and R3 in your routines and your assembly functions. Any other registers that you modify need to be saved. That's the standard convention. Now, if you're calling assembly routines from assembly, you can come up with your own convention, right? If you're calling assembly routines from C, you have to follow the C standard calling convention. Or if you're calling C functions from assembly, you have to follow the C standard calling convention. But you know, if you're writing an assembly, calling assembly, you can pass parameters in the registers using all the registers if you want. You can pass on the stack. But usually it's recommended that you follow the C standard calling convention. And then one other thing that I briefly want to mention, then we'll look at the exercise. I'll do it over here so I don't have to erase. One of the other topics in this chapter is actually how floating point numbers are represented. We haven't talked about that. We've spent some time talking about how integers are represented, you know, positive and negative integers using 2's complement. This particular microprocessor has a floating point processor. That's not always common to have a hardware floating point processor. In microcontrollers that don't have a floating point processor, there's usually a library of routines that can manipulate the values to provide, you know, to do floating point arithmetic. Okay, but it's slow if there's not a hardware floating point processor. And that's often true in embedded systems. Again, this microcontroller is pretty nice. It has a hardware floating point processor, but a lot of them don't. And so if you use floating point arithmetic, it can often be very slow. A workaround is to use what's called fixed point arithmetic and use fixed point numbers, where we can approximate floating point numbers actually using integers and fixed point notation. So, and it's a pretty simple concept, actually. The fixed point representation of a floating point value x is, and I'll call the fixed point representation x bar, where this delta is usually a power of 2, so 2 to the n, or a power of 10. Okay. 10, 100, 1,000, 10,000, whatever. Okay. It's actually a little faster if delta is a power of 2, because then you can multiply by delta just by left shifting by 2, by a number of bits to get whatever power you want. So consider temperature conversion. Where F is, we're converting from Celsius to Fahrenheit. So the formula is F is equal to 1.8 C, 9/5 C plus 32. And normally you would use floating point numbers for C and F so that you could have, you know, 10th of degrees or even 100th of a degrees. But we can do this actually using a fixed point representation. And here your delta might be 1,000 or 100. You know, if you used 1,000, then C and F are really stored in millidegrees, okay, thousandths of a degrees. In this example, I just arbitrarily chose a delta of 100 to represent F and C. So my formula becomes 1.8 C plus 3,200. 32 is a temperature. So if I'm going to keep F and C, you know, stored in fixed point as, you know, their floating point values times 100, And when I have to add this 32, I really have to add the 3200. The 1.8, that's a multiplication. That doesn't need to be converted. That's a scaling factor. I could use a larger delta here, but what this means is a temperature of 88 would actually be stored internally as 8800. It would be stored in binary, of course, that's the decimal representation, but it would be stored in as the corresponding binary number 8800. Okay. Now here, this is just me and the program design deciding how I'm going to store F and C as integer values instead of floating points. So F bar and C bar here are integers, 32-bit integers probably. Whereas F and C would be typically floating point numbers. I would still want to be able to carry out this operation using integer arithmetic. That's the whole advantage of using this integer representation. In this case, it's easy. We can implement the formula using only integer arithmetic as F bar is 18 times C over 10 plus 3200. And that's pretty simple. Here's a slightly more complicated example from the problem from the textbook. It's a digital filtering problem. This is problem 7.22. And we're asked to implement this particular digital filter using fixed point notation. 9 x1 plus 0.8000. And also convert this operation to an integer operation. Now, X is my current, represents my current input. Y is my current output. X1 and Y1 are the previous input and output. So this output actually depends on a previous value of the output. So it's relatively easy to implement in C. I'll show you that, but the trick here is actually trying to do this without using floating point numbers. And he also points out in this statement, and this is to help with converting the formula to integer arithmetic. An easy way to do this, if you can't figure out a simple representation, is just multiply all of these by 1,000 and then divide by 1,000 at the end. But he gives us as a hint, this is 1/9. This is actually 4 divided by 45, 0.8889. And this last one is 4/5 y1. I chose to let, I think, delta be at 1,000. We'll look at the code in just a second. But the formula is actually the same because I'm not adding any values. I have to do the same scaling. Okay, so this is the formula using the fixed point representation, where my fixed point numbers are 1,000 times their floating point values, the corresponding floating point values, and then I just truncate them to integers. And then now I can implement this using only integer arithmetic. If I just multiply by 45, this becomes 5x bar plus 4x1 bar, and then this is 36 y1 bar, and then divide by 45. Now I put on the website, but I'll show it here in just a second, but you can download this program later. Someone actually deleted the C compiler on this machine. I found out just before class. These rascally students probably. Unfortunately, it's probably some other professor. So I had to actually log into CS Server and just use the compiler there. I'm just using a C compiler. We could do this in Code Composer Studio, but I chose not to, I guess. Okay. So what I did with this program is, it's frozen. No, it's not frozen. It's on the wrong display. How's that? Is actually just implement this in floating point. So this is the YF for floating point. And then also implement it using fixed point integer arithmetic. And that's the YI and the XI stuff. And then he tells you in the problem that the X values are all between 0 and 1028. So I just chose to let X be a constant 512. Now, in the delta value I used was 1,000. Okay, you could use 10,000. One thing you have to be sure to try to avoid that if you make delta too large, your formula could possibly overflow the 32-bit integer representation you're using. So, but I just used 1,000. These are initializing the previous input and the previous output. So this is setting the initial conditions really. But then in the loop, this is setting the floating point input, the 512, the integer, the fixed point integer representation of that is 512 times 1,000, so it'd be 512,000 in XI. Of course, the floating point representation for YF is straightforward. It's the same formula that's given. So you compute YF, and then you update the previous input is the current input, and then the previous output is the current output, and then we loop around again. Okay. And then down here at the bottom, it prints out YF, the floating point value, and then it prints out our fixed point value as well. So same formula for the fixed point is, we've converted these to actually integers. So if you run this, so these are the values computed using the floating point representation. And these are the fixed point values. Okay, so these are nothing, these are all computed using only integer arithmetic. Okay. And remember with the scaling factor that these are supposed to be 1,000 times larger than the floating point values. And you can see that the fixed point actually does a really good job of maintaining about the same accuracy as the floating point. Now again, it's not something often, certainly students in computer science, programming a desktop computer would probably never even think about this as an issue, right? We've got a PC with a floating point processor, they're incredibly fast, but programming embedded systems, that's not always the case. And you may not have a floating point processor. Even if you do, the arithmetic using the floating point processor is still usually slower than using just integer arithmetic. If you don't have a floating point processor and have to do some computation, you almost certainly have to do some fixed point processing. A lot of really fast processing machines, like graphical processors, actually do all of the arithmetic using fixed point representation instead of using floating point numbers. Again, we'll talk about floating point number representation actually on Monday. It takes a little effort to convert your arithmetic into, fixed point representation, but usually not a lot of work to do that, unless the algorithm's really, really complicated. Okay, so yeah, we should have enough time. So I want you to go to the course website too. We'll create a new project. I'm just going to call it Lecture 28 Assembly. And we'll create an empty project because we're going to download the main file. And I forget where the workspace is on this machine. Users AR63. Okay. So now on the course website, there's 354, and today's lectures, and then download this main.c and this average.c into that project folder you just created. So save link as. I have that somewhere. Lecture 28 assembly. So save that there, and then save the average.c there as well. So if you take a look at this, this is one of the problems in the textbook. He has you write a routine. The problem is to write a routine in assembly that computes the average of a 10-element array of unsigned integers. So here's the cheater way to do that. You write it in C. That's pretty easy to write it in C. This is the C representation. Again, it's supposed to return an unsigned int. It gets an array of unsigned ints. So we're told that it's always going to be of length 10. So I just sum over the 10 elements, computing the sum, and then return the sum divided by 10. So I'm not, this should compile at this point. Should, I thought I saw some sort of error message. Oh, that's because it does print out, so we have to include the uart.h and the uart.c in our project. So add files. So go into the source And then you have to add both of those to the project, link to them again. And now if we build, hopefully the errors will go away. Okay, so normally, the compiler compiles our C code directly to object code. You can optionally have it produce the corresponding assembly. So the way you do that, you can either right-click here on the project, or you can go up to the project menu and select properties. And then down here in advanced options, so it's build, ARM compiler, advanced options, expand that. Look for assembler options. And then check this little box that says keep the generated assembly language. You can also generate a listing file that has even more detail, but we don't need that. The other thing that you want to do, well, I'll show you what happens. If we do that now, okay, and then rebuild. Okay, there's one other change. You don't need to follow this. There's one other change that we want to make, and I just want to show you why we want to do it. So now after this finishes building, if I look in, I'm doing the debug release. So if I look in the debug folder, I should see an average.asm file. Okay. Now, the assembly is actually embedded in here, but it's got literally hundreds and thousands of lines of debug information in this file. So it makes it really tough to pull out the assembly that I'm interested in. So make one other change here in the properties. Under advanced options, where it says advanced debug options, over here in the menu where it says debugging model, pull it down and say suppress all symbolic debug generation. And then apply. Now build the project. Yours is probably a lot faster than this machine. I didn't build it. I sent it to the debugger. I screwed up. Okay. I meant to just build. Clicked on the wrong icon. I might have to, I don't think it did. I need to clean and rebuild. I don't think it's actually going to overwrite the assembly it generated. Now let me try it. Okay. So now if we look in the debug folder, at this average.asm file, it's still got some information that's not pure assembly in the file, but it's got some stuff now that looks like pure assembly. Okay. Not that many lines. Okay. So what we're going to do is close this and actually copy it and then paste it into the main folder. Now, I think if we build at this point, it will actually link in our assembly version instead of our original C version. You can guarantee that by actually right-clicking on average.c and then excluding that from the build. You don't want both of them to be build because it's defining the function twice actually. So, but now if we build again, actually expand the console. If you look up here, you should see it's building from. Did I hit the debug thing again? Hitting the wrong. But now you should see it's actually building from average.asm instead of average.c. Okay. Now, a couple things here. Assembly files for this compiler can have either of two extensions, a .s or a .asm. If you recall, we were using .s at the beginning of the semester. So that's no big deal. You can just, if you want to change that, just rename the file. So it's .s instead of .asm. But more than that, if we look in the file, there's a lot of comments here. You know, anything that begins with a semicolon. So we can kind of get rid of to clean this up a little bit. Gonna be careful. Let's see, let me get rid of, I'm gonna get rid of all this stuff down at the bottom. Okay. You don't actually need this compiler line. The C link is C linkage. I think it does that by default. You can see what you can get away with deleting here. At some point, you're going to delete too much, and it's going to give you an error. You're going to have to go back, but I think this is fine. The other thing that's a little odd, if you look in the assembly, is this is part of a loop, a branch if not equal loop, and this is back to a label. It's a strange looking label, right? It's because it's an automatically generated label by the compiler. You know, every loop would have, you know, some sort of label like this, but instead of L1, it's probably L2 or L3 or L4 or L1000, depending on how many loops you have. You can now bring all your assembly knowledge to bear and give it a more meaningful name, like loop 1. And I'm not going to say that's much more meaningful, but you know. Now that's changing the label. You also need to change any references to it. And it uses, again, strange labels. It has absolute value bars, but here it's just loop 1. Notice anything else strange about this assembly? About the registers? What registers is it using? Yeah, it's got a bunch of A registers, right? I never talked about actually this processor having any A registers. Unfortunately, this compiler uses register aliases, and I mentioned that on the handout here, that they use A1 through A4 to refer to what they call the argument registers, which are the same as R0 through R3. I find it really annoying, one, because of the off by 1 thing. R0 actually maps into A1. And you know, we've been thinking in terms of the native registers instead of the alias versions. registers R4 to R11 actually are mapped into V1 to V8, and they use V to represent the variable registers. Okay. Remember, R1 to R3 are used to pass arguments. So you can change that if you want pretty easily. Just go into find and replace every instance of A1 with R0. Replace all. And A2 would be replaced with R1. Now don't screw this up, because if you make a mistake and then go try and go back and fix it, I mean, you may have, A3 should be R2, replace all. And then A4 is R3, replace all. Now it looks a little more familiar. Okay, we may even be able to figure out kind of what's going on with this. Remember, the address to our array was passed in R0. First thing, this is the assembly generated by the compiler, right, from our C. You might write this completely differently, and that would be okay. But we do know that the R0 register contains the address of the array. Now, normally here, we would push onto the stack any registers other than R0 through R3 that we were modifying. But notice this little routine only uses R0 through R3. So we don't have to save any other registers. We would normally save the link register on the stack if we called a function, but we're not calling a function here either. So we don't really have to save anything on the stack. R0 is moved into R1. R2, I'm guessing, is being used as our sum variable, right? We remember in our C, we had a line there that says sum is equal to 0. And then R0 here is now being used as our counter. We're counting from 0 up to 10. Now this is loading from this address where our array is into R3. So this is the current element. And if you remember this addressing mode, then actually increments R1 by 4. So it will automatically be pointing to the next element in the array. And then subtracting 1 from our count. Okay, so this is the decrementing the count. And then we're adding the array element into the sum and storing it back in the sum. And then now the branch if not equal is actually going back to the subs, okay, because it was, here's the S that says change the flags register. The add doesn't have the S, so it's not actually changing the flags. So we're branching if R0 is not back to 0, it started at 10, we're branching back the loop and then repeating that, getting the next element out of the array. And then we're moving the last part of the C program, if I can look at it, is dividing by 10. So it's moving 10 into R0, and it's dividing R2, which contains our sum, by 10 and storing that back in R0, because our return parameter has to be in R0. And then this is the final return from function. I mention this because this is a great way to actually learn assembly. If you're curious about in C, you know, where a particular variable is being stored, you know, maybe where a global variable is being stored or where a constant variable is being stored, look at the assembly, the corresponding assembly file. This is actually how, you know, we started the semester, and I gave you an assembly file. This is how I generated it. I didn't tell you that. I was trying to make you think I was pretty smart. I just cheated like this and had the compiler generate it for me. Actually, I think that does make me pretty smart. So, but actually just had the compiler generate it. And I do this for actually every new microprocessor I work with. You can dig through all the documentation to find out what the format of the assembly file has to be, or you can have the compiler generate it for you with all the appropriate sections. So then the next thing I did was actually go back and stick string constants in the C look at the corresponding assembly to find out where they were stored. So then, we had the next version that had the string constants in it. We could see and how other constants were stored. So, but here again, you can see that the compiler isn't magic. It has to do a lot of work. But hopefully at this point, maybe you can see exactly how the C that we started with translates directly into this assembly language. And again, it would be interesting to look at this, maybe when we passed in more than 4 arguments, or where it was forced to actually push some values on the stack, or whether or if we called another function from within average, and then we'd see that the link register actually has to be stored on the stack as well. All right, that is it for today. So have a good weekend, unless I see you in a couple hours and 3:10. Can't have a good weekend yet.